Hello, everybody, and here we are, lesson 5.4 in your textbook on page 309, and it's about exponential growth and decay. And we have watched lessons previously in this chapter where you need the information, you need to know what I have showed you to understand what's going on. So please watch the lessons one by one, not mix and match, okay? So exponential growth and decay. Let's underline the title. So growing means something is getting bigger. Decay means something is getting smaller. An initial amount. Growth means bigger. And today we're going to learn, the objective is to model exponential growth and decay. Model is always another word for word problems. So we're going to look at real life problems where we can use growth and decay. And by the way, most of these problems are real life problems. A lot of math like this is used in business, banking, science. So this is where, excuse me, you're starting to see where it's relevant to our real life, okay? So on the bottom of the page, here's the chart we're gonna look at. Essential understanding: an exponential function can model growth or decay of an initial amount. This is always your starting amount. The equations still look like this. Y is equal to a number A times a number B raised to the power of X, where this first number is your initial amount, and this number B, think of B as base, as your X, as your power here, is your growth or decay rate. Yeah, this is how fast it grows. Okay, so let's look at growth first. So this chart is on growth. Decay comes later in the lesson, okay? Remember from the previous lesson, this is a growth, exponential growth graph. It's curved, it goes uphill, it's gonna grow faster and faster. Here's our y-intercept, which is always the initial amount, A, where X is 0. This is a very important point. And B, the base has to be bigger than 1. It cannot be 1 or negative. It has to be bigger than 1. All right, so let's read this. Exponential growth can be modeled by the function, there it is again, I'm just rewriting this from here to here, where A is positive, that's what this means. Bigger than 0 means if a number is bigger than 0, it's positive, and B has to be greater than 1. If it's growth, B has to be bigger than 1. Okay, so this number must be bigger than 1 to model growth. The base B, this number right here, is the growth factor, which equals 1 plus, here's the key, it starts out with 1, but you add the percent rate of change to it, expressed as a decimal. Very important, decimal. Okay, so for example, if it grows 4%, you take the 4, you put zeros in front, and you move your decimal back twice. So that would be 0.04 as a decimal. You always move the decimal to the left twice to change from percent to decimal, okay? And down here, it explains it one more time, really beautiful, the whole thing. Here's our initial amount, here's our base, which is the growth factor if it's bigger than 1. This is always our exponent, which is our variable, and this is our answer, y. Okay, so on the next page, I'm going to show you another calculator because I've used my calculator as a photo, but you might be using the calculator on your phone. And in class, you're not allowed to do that. So I urge you to get used to a calculator that's not your phone, but maybe your phone looks like this. This right here, zoom in, is your power key. So if you want to put in 5 squared, you would put 5 power 2 equals, or 5 cubed, 5 to the power of 3, 5 power key 3 equals. By the way, this is your square root key, which is the opposite of taking a power. You're undoing the power with the square root. With the power key, the numbers get bigger. With the square root key, the answers get smaller. This is a good key to use because it stores the last answer. So if you don't want to retype all the decimals and you need to do another operation with your last answer, you just push that button and it recalls that last answer and you don't have to retype it. Okay, all right, let's get started on our lesson. And we are on page 310, and I'm doing the problem in the middle of college enrollment. And here we are, number 1, college enrollment. The number of students enrolled at a college is 15,000 students. This is your initial value, A. I'll put the A above it in our equation. Remember, the equation always is modeled after A times B to the power of X. A is your initial amount, B is your growth or decay factor. This is a variable X, any number goes for that, and this is your answer Y when you evaluate all this. And it grows, good, we're gonna have a growth factor of 4% each year. So the first thing I'm going to do is change the percent to a decimal. Don't forget that. So we're not using that, we're using this number, okay? So on the side here, I want to give you a little, this is for you to kind of remember. So for growth, it's Y is equal to our initial amount times 1 plus the percent in decimal raised to the power of X, right? The 1 plus a number makes it bigger than 1. For decay, so let's make, for decay, later we're doing decay, you use the formula Y is the initial amount times 1 minus the percent to the power of X, which changes this to a number less than 1, which grows, gets smaller. So these two, the plus and the minus, is the only difference. Growth, you add the percent. Decay, you subtract the percent from 1. It's always the 1 here. And don't forget, the percent has to be a decimal. So let's fill this out. The initial amount, so they're kind of leading us through this problem, which is why I like it, 15,000 students. The percent rate of change is 4%, so the growth factor B is 1 plus 0.04, which is 1.04. Try it in your calculator if you don't believe that. So this is your growth rate, okay? To find the number of students enrolled after 1 year, you calculate 15,000 times 1.04. So then I'm gonna do that. I never figured that number out. 15,000 times 1.04. So it's 600 more students in 1 year. Oh, what happened? Oh, no. So in 1 year, they added 600 students. Notice that? With a 4% growth rate. Complete the equation y equals blank times blank to the power of x to find the number of students enrolled after x years. So now we're going to come and finish that up. Y equals A is 15,000. And instead of times, I like a parentheses to the power of x. And there's the equation after x years. All right, so this is the equation I can use to find the student population after any years have gone by. So now they're going to use this equation. So the equation is right here. Use your equation to predict. We can predict with these equations. That's why we write them. Yeah, the number of students enrolled after 25 years. So that's important. We want to know how our college is growing. We need to plan on new buildings, bigger facilities. So you don't want to plan too small. So we're going to plug in for X 25 and use our calculator, right? Because X is the number of years. So Y is the number of students, 15,000 to start with, growth factor to the power of 25. Use your calculator. You can put this whole thing as you see it in your calculator, 15,000 times, you know what, I like the parentheses. Your calculator has parentheses, I think. Let's see. Does this one have parentheses? Yeah, right there. They all do. So the parentheses mean times. So you just follow that along. And I'm gonna urge you to use your calculator right now and not just watch me. And then my power key looks like that, 25 and then equals. Don't forget to push the equal sign. Some students don't do that. They're like standing there like deer in a headlight. Oh, what, the number isn't coming. And now I have the answer. So you have 30, and then you have to round because people, there's number of students. You can't have part of a student. So since I'm rounding, I'm changing this to the squiggly is about 39,988 students after 25 years of growing. Now, the only thing is the growth rate has to stay the same. So if they grow every year 4%, then that number is correct. But if their growth rate changes, then the whole model changes. Okay. It's next page. So this is in the middle, we're on page 311. So this is interesting. I don't know how much you know about banking, but if you bring money to a bank and invest it like in a savings account, they pay you interest. And the interest means you get a little bit of money each month or every other month added onto your money that you already got. And it's not much, let me guarantee you, but then when they add that money, the next time they pay interest, you have your original initial amount plus the interest they already paid you. So now you're making interest on the interest. That's called compound interest. Yeah. So we're learning now about compound interest. When a bank pays interest on both, the principal, by the way, the principal is not the school principal. This is how much you invest initially, your deposit. The money you take to the bank is your principal. And the interest an account has already earned, the bank is paying compound interest. Yeah? Compound interest is an example of exponential growth. You can use the following formula to find the balance of an account that earns compound interest. Very complicated looking. Don't worry, all these pieces are explained, right? A is your balance. How much do you have in your account at any given time? P is principal, which is your initial deposit, right? That capital P. Then comes your growth rate. R is the interest rate, yeah, and it's expressed as a decimal. And then N is the number of times interest is compounded per year. So maybe every month, that makes it 12. Every 3 months, that makes it 4, because every 3 months you get 4 of those increments in a year. And T, this little t is the times in years. So let's say in 5 years, you want to know how much money you got in your account. That T would be 5. So that's that formula. And guess what? We're going to work on that formula. And don't be afraid. It's not that bad. Okay? Use your calculator. Think, is the compound interest formula an exponential growth formula? Yes, we already saw that up here. Compound interest is an example of exponential growth. Hopefully, when you bring your money to the bank and you start a savings account, it'll grow and not get less, okay? So here we are. Suppose that when your friend was born, Your friend's parents deposited $2,000 in an account paying 4.5% interest, compounded monthly. That means N is 12 because it says here, N is the number of times interest is deposited per year, 12. What will the account balance be after 18 years? So that means T is 18. What else? Oh, 4.5%. We need to change it to a decimal. So you can add zeros in the front and move it twice. 0.045. This is the number we're going to use. Now let's put it all in. A is the amount that you will have. Initial amount is 2,000. 1 plus R is 0.045 over, this is a fraction, N is 12 since they were compounding it every month. Close the parentheses, I'm here. This is a power, so this is raised to the power of N times T, 18 years. So this is how the formula looks when you plug it all in. Now don't despair, we're gonna work this out one by one. First multiply 12 by 18 and find out this number right here. So I'll make it red. So you wanna multiply 12 times 18 and you can put this in your calculator. This, by the way, is a division, divided by 12. You put it in your calculator as you see it. 1 plus 0.045 divided by 12 equals, okay? Don't forget equals. So then I'm going to rewrite, start with the initial amount. The parentheses turn into 1.00375. Please do it yourself. Try this. It might take you a few minutes. You've got to figure it out. 12 times 18 is 216. So my exponent here is 216. Now put all this in your calculator. So the amount, 2,000 times, open parentheses, this long number, close parentheses, raised to the power of 216 equals, and it's money. So I put a dollar sign, 4,489.01, which is 1 penny. $4,000, $4,489.01 is in the account after 18 years. So it more than doubled. All right. So that's compound interest. And now we're going to the next page, which is on decay. Is that a blank page? Yeah. Okay, we're on page 312. Look at that. It's decay. It goes down. The graph gets smaller, smaller, smaller until it never goes to 0. That's that asymptote. It always gets smaller and smaller. So let's look at decay. We already know so much about these graphs, hopefully, that hopefully this is something that you now are understanding. Here's our model, initial amount, growth, decay factor, power of X, exponential decay, rate of change. The value of B tells if the equation models growth or decay. B bigger than 1 is growth. B between 0 and 1 is decay. So it's all about the base. Isn't there a song about that? It's all about this B, okay? That tells you that. It's restating that, see, exactly like that. The base B is the decay factor, which equals 1 minus the percent rate of change, expressed as a decimal. Just like I showed you on the previous page in the little margin. Where was it? There. Yeah, minus, there we go, decay, 1 minus the percent. That's the only difference. Growth, 1 plus the percent. decay 1 minus. So where are we? Okay, back to this page. Yeah, I don't know what else to say about it. Hopefully, you're seeing a few things now. Maybe things will click as much we do this more. Function, initial amount, base, less than 1 is decay, and our function gets smaller. Yeah. All right, let's see. We're going to do problem 5 on the next page. Identify the initial amount and the decay factor in this function. This is your initial amount, 10, what you started with, and this is your decay factor. By the way, that decay factor tells me that the decay is 90%, because it's 1 minus 0.9 gives you 0.1. Okay, so that's easy. That was done. There's just one to see if you understand that, and I gave you some of these for the homework. So make sure you look at all that. And now let's do one more problem, number 6, population. Population is very good about growth or decay, because this is, we always double in population. The population of a city is, no, we don't really always double, but the world population is doubling every so often, every like 40, 50 years. The population of a city is 45,000, that's the A, and decreases 2%. 2%, do not use that number, 0.02. That's your decay factor minus. Each year, if the trend continues, what will the population be after 15 years? So I'm going to write my equation with different variables. I'll call the YP because that's the population, just to mix things up and show you you can do that. 45,000, my 1 minus 0.02 raised to the power of T. T stands for time. Yeah, there you go, time, because it's years. So now I'm going to subtract this from 1. So the population. So I want to make my parentheses just one number. And that's that number. And there's my equation. So this equation right here can tell me the population of this town at any year after we start counting. And you're going to plug in for T15 to find out how many people are in this town after 15 years. Think about it, should it be more or less people than they started out with? Of course less, right? Because it's decaying. So I'm going to put 15 here. So I want you to use your calculator, put that in, 45,000, parentheses, 0.98, close parentheses, power 15 equals. And you will get 33,236 people rounded. You can't have part of a person. So there's that. See how that works? And then one more problem on the next page, which is how to write the equation. So if you are faced with a problem of looking at a graph or a table and you have to come up with the equation, which it's not easy, so please don't despair if you're like, I never get this. I don't know if I gave you a homework question on it, but I think it's interesting. The only thing you need is the y-intercept and one more point. You always need the y-intercept, which is this one, and one more point. So you can pick any other point if it's the table. I'm only going to do B, but if you look at the table, you have to have the y-intercept and one more point. So 2 points, one of them being the y-intercept, will help you write the equation. So I'm doing B, okay? We're not doing this one. So here's the shell. You need to find A and B. Those two numbers need to be found. So start with the y-intercept, x, y. Y is 2 and x is 0. So I'm plugging those two numbers in my equation. So anything to the power of 0 is 1, so A is 2, which is your initial amount, which makes sense, right? So A is 2, so I can plug in for A2, but I still need B. Now B is the growth rate. It's a growth function here. So look at the y, from 2 to 6, it triples. You can already see that B is going to be 3 to the power of x. But if you don't understand that concept, or if the numbers are not as clearly connected, you can do this. So now you found A is 2. So let me show you what else you can do. 2 times, we still need to find B. So I take the other point, xy, xy, the second point, I plug that in. Y is 6. 2 times, we still need B, x is 1. B to the power of 1 is just B. Divide by 2, B is 3. So now I have B, I plug that in, and my equation is there. 2 times 3 to the power of x. So remember, you need the y-intercept and one more point. And in our class, you do need that 1 because we don't know how to solve other equations other than 1 here. But in a higher math class, any other point will do. But in this case, 1 really works well and the 0 works well. So start with the 0 and then plug those numbers into your shell, and then you need A and B. Anyways, that was that. And I'm going to show you what you got to do for homework next. Homework is on page 315. You're going to do number 9. What is the growth factor? Number 10. What is the initial amount? Always refer back to your lesson. I showed you all of these, and you need to find them and look at them if you forget. Number 11, what's the decay factor? Number 12, now you have to think a little bit, not quite as easy. Still asking for the decay factor. Number 13, ooh, this is the compound interest problem. See if you can tackle that one. And then the next page is number 14. How can you tell if a function models growth or decay? You should be able to answer that one really easy. It's quick. And then on the bottom here, I decided to just ask you if you can tell whether the functions are growth or decay or neither. So all your answers should just say growth, decay, or neither. That's all you have. And you just look at the function. You don't need to graph them. You can just, if you listen to the lesson and you took notes and you studied your notes, you should be able to answer these really quick. I think that's it. No, there's one more, but I don't know if I got it on there. Car value, why isn't it there? I guess not. Huh, because it didn't copy. Well, you're lucky. The last question, I wanted you to do 23 on page 317, but it didn't copy. But you can try it. It's about the car value. I'll see you later. Bye.